June 30th, 2026. Today is a day that the United Nations has designated as International Asteroid Day, a global campaign to raise awareness about the threat of asteroid impacts and the importance of planetary defense. But this is not just any asteroid day. Today marks the 118th anniversary of the most mysterious and powerful cosmic impact in recorded history. On the morning of June 30th, 1908, something exploded over the remote Siberian wilderness near the Podkamennaya Tunguska River. It flattened approximately 2,000 square kilometers of forest, an area roughly the size of Tokyo, and destroyed an estimated 80 million trees. Witnesses reported a brilliant fireball brighter than the sun, a deafening roar, and a towering column of smoke rising into the atmosphere. Seismic instruments hundreds of miles away detected the shock wave, and yet there was no crater. There were no large meteorite fragments. The object that caused the Tunguska Event, as it came to be known, simply vanished, leaving behind only flattened trees and a mystery that has captivated scientists for over a century. Now, on this same day, June 30th, 2026, another cosmic mystery has just been solved. Chinese scientists, using the MeerKAT radio telescope in South Africa, have detected radio pulses for the first time from a young neutron star known as a Central Compact Object, or CCO. For decades, these objects, which sit at the centers of supernova remnants and shine brightly in X-rays, had remained entirely radio silent. No radio pulses had ever been detected from any CCO since pulsars were first discovered in 1967. The question was, are these objects intrinsically silent, or are they simply too faint to detect with existing technology? Today, we have the answer. Using extended, targeted tracking and advanced digital processing to filter out cosmic background noise, the research team detected a faint radio pulse repeating every 424 milliseconds. They have named the newly active star the Blue Eye Pulsar because combined radio and X-ray images revealed a distinct eye-like blue shape. This breakthrough, published in the journal Nature Astronomy, provides crucial evidence for understanding the formation and evolution of young neutron stars. It challenges the conventional view that CCOs are natively quiet, proving that even young neutron stars with relatively weak magnetic fields can emit radio pulses. It also suggests that a vast number of faint young pulsars may still be hidden across the Milky Way. These two events, separated by 118 years, are connected by a single, profound idea. The Tunguska Event, the greatest cosmic impact in recorded history, and the Blue Eye Pulsar, a dead star that has just started whispering to us across the cosmos, both remind us that the universe is not a static, predictable clockwork. It is a dynamic, violent, and astonishingly creative place. It is a place where objects from space can reshape the surface of a planet in seconds, and where the remnants of exploded stars can, decades after their death, suddenly start broadcasting signals that we can detect with our most sensitive instruments. This is the universe that Richard Feynman loved, a universe that is not safe, not predictable, but endlessly surprising. And today, on June 30th, 2026, we are witnessing both the anniversary of one of its greatest mysteries and the solution to another. Let us begin with the Tunguska Event. The explosion occurred at roughly 7:15 a.m. local time on June 30th, 1908. The region was sparsely populated, inhabited largely by Evenki reindeer herders. Their descriptions became the first record of an event that scientists would spend the next century attempting to reconstruct. Those nearest the blast said they were thrown into the air, some losing consciousness as homes were damaged or destroyed. Others farther away described seeing a towering column rising into the atmosphere. Herds of reindeer reportedly perished. The blast took place roughly 4,000 kilometers east of Moscow, near the Podkamennaya Tunguska River in what is now Krasnoyarsk Krai in Russia. Today, scientists believe the object entered Earth's atmosphere at an angle of roughly 30 degrees before exploding at an altitude of approximately 10 kilometers. Instead of striking the ground intact, it released an enormous amount of energy in the atmosphere, an airburst of staggering proportions. Estimates of the energy released range from 10 to 30 megatons of TNT, roughly 1,000 times more powerful than the atomic bomb dropped on Hiroshima. But here is the problem. Despite repeated expeditions, no one has ever found a crater or substantial meteorite fragments. The remoteness of the explosion delayed scientific investigation for almost 20 years. Additionally, World War I, followed by the Russian Revolution and Civil War, diverted attention away from the isolated Siberian wilderness. In 1921, the Soviet Academy of Sciences dispatched geologist Leonid Kulik to the area, but he was unable to reach the site because of the difficult terrain. Only in 1927 did he finally arrive. Even after 19 years, the forest still bore unmistakable scars of a big explosion. Near what would later be identified as the epicenter, trees remained upright but had been stripped of branches and bark. Many showed signs of burning. Yet despite repeated expeditions, Kulik never located the crater or substantial meteorite fragments that many expected to find. The mystery deepened. What was the object? Was it an asteroid? A comet? Something even more exotic, like a piece of antimatter or a miniature black hole? Over the years, scientists have proposed a bewildering array of explanations. Some suggested that the object was a stony asteroid that exploded in the atmosphere, leaving no large fragments. Others argued that it was a comet, a dirty snowball of ice and dust, which would have vaporized completely upon entering the atmosphere, leaving no trace. There were even suggestions that the Tunguska Event was caused by a burst of antimatter from space, annihilating upon contact with the Earth's atmosphere, or by a tiny black hole passing through the planet. Each theory had its proponents, and each theory had its problems. The truth, as is so often the case in science, is that we may never know for certain. As Dr. Mark Boslow, Research Associate Professor of Earth and Planetary Sciences at the University of New Mexico, told NDTV, "We know with high confidence that it was meteoritic airburst. There is still a large uncertainty in the magnitude of the event." I use the word meteoritic to generically refer to either asteroid or comet because we don't know which it was. We know precisely when it happened and what direction it came from, but we do not know its speed or physical properties of the object. The uncertainty is part of what makes the Tunguska Event so compelling. It is a reminder that the universe does not always give us easy answers. Sometimes it gives us a puzzle that we can only piece together slowly, over decades, using the best tools and the best minds we have. Now, let me take you to the other side of the story, the discovery of the blue eye pulsar. This is a story that begins in 1967, when Jocelyn Bell Burnell, a graduate student at Cambridge University, discovered the first pulsar. Pulsars are rapidly spinning neutron stars that emit regular beams of radio waves, like cosmic lighthouses. The discovery of pulsars was a revolution in astrophysics, and it earned the 1974 Nobel Prize in Physics for Anthony Hewish, Bell's supervisor. But among the known neutron stars, there has always been a special subclass, central compact objects, or CCOs. Located at the centers of supernova remnants, they shine brightly in X-rays and exhibit multiple hallmarks of young neutron stars, yet they have long evaded detection in radio wavelengths. These objects were designated as CCOs, and they were a puzzle. Were they intrinsically radio quiet, or were they merely too faint to detect with existing technology? For decades, the answer remained elusive. Then came the MeerKAT Radio Telescope in South Africa, a precursor array of the Square Kilometre Array, or SKA, one of the most ambitious scientific projects in history. MeerKAT is a radio telescope of extraordinary sensitivity, capable of detecting the faintest whispers from the cosmos. Using this instrument, a team of scientists from the National Astronomical Observatories of the Chinese Academy of Sciences and the Department of Astronomy of Tsinghua University conducted an in-depth search for multiple CCO targets. For the first time, they detected a radio pulse signal with a period of approximately 424 milliseconds emanating from the prototypical CCO at the center of the supernova remnant. The signal came from 1E1207.4-5209, a typical CCO located inside a supernova remnant named PKS 1209-5-1/52. The discovery was made possible by MeerKAT's exceptional sensitivity and a specialized observation strategy. The team used extended targeted tracking and advanced digital processing to filter out cosmic background noise and extract the extremely weak signal. But the story does not end there. Researchers also discovered that in 2025, the neutron star underwent a significant spin glitch, an abrupt, sudden increase in its rotation speed. Scientists speculate that this sudden shift may have disrupted and reshaped the star's magnetic environment, effectively turning on or boosting the radio emissions that were previously invisible to observers on Earth. It is as if the star, silent for thousands of years, suddenly decided to speak. The discovery challenges the conventional astronomical view that CCOs are natively quiet, proving that even young neutron stars with relatively weak magnetic fields can emit radio pulses. It also suggests that a vast number of faint young pulsars may still be hidden across the Milky Way. Now, you might be wondering, what does a 1908 explosion in Siberia have to do with a 2026 discovery of a pulsar in the constellation of Centaurus? The connection is deeper than you might think. Both events are about the sudden, unexpected release of energy from cosmic objects. The Tunguska Event was a release of kinetic energy, the energy of motion, as an object from space slammed into our atmosphere at tens of thousands of kilometers per hour. The blue Eye Pulsar is a release of electromagnetic energy, radio waves, as a rapidly spinning neutron star, a remnant of a supernova, beams its signal across the cosmos. Both are reminders that the universe is not a quiet, peaceful place. It is a place of explosions, of collisions, of sudden and violent events, and both are reminders that our understanding of the universe is always incomplete. There is always something new to discover, always a mystery waiting to be solved. Feynman understood this better than anyone. He was a man who was never satisfied with the easy answer. He was a man who loved a puzzle, who relished the challenge of figuring out how things worked. He would have been fascinated by the Tunguska Event, the mystery of the missing crater, and the debate over whether it was an asteroid or a comet. He would have been thrilled by the discovery of the blue Eye Pulsar, the proof that a radio-silent object could suddenly start broadcasting. And he would have appreciated the deeper lesson of both events, that the universe is not a static, predictable machine. It is a dynamic, evolving, and endlessly surprising place. It is a place where the unexpected is the norm, and where the most exciting discoveries come from the things we do not yet understand. There is a third element to today's story that I want to bring to your attention. June 30th, 1905, exactly 3 years before the Tunguska Event, Albert Einstein submitted his paper on the electrodynamics of moving bodies to the journal Annalen der Physik. This paper set out his theory of special relativity, one of the most revolutionary ideas in the history of physics. It shattered the foundations of physics, overturning centuries of Newtonian thinking about space and time. Einstein was working at the Swiss Patent Office in Bern at the time, examining inventions for their patentability. In a letter to his friend Michel Bessot, Einstein regarded the patent office as that secular cloister where I hatched my most beautiful ideas. The most profound of these ideas emerged in 5 theoretical papers written in quick succession in 1905, a year that historians would later refer to as Einstein's Annus Mirabilis, or Miracle Year. His first paper described the particle theory of light, which would later earn him the 1921 Nobel Prize in Physics. His second created a new method for determining molecular sizes, and his third examined Brownian motion. The special relativity paper was the third of these, and it was a bombshell. It proposed that the laws of physics are the same for all observers in uniform motion, and that the speed of light in a vacuum is constant for all observers, regardless of their motion. This led to the stunning conclusion that space and time are not absolute, but relative. Time can slow down and space can contract, depending on how fast you are moving. It was a radical departure from the physics of Newton, and it laid the groundwork for the development of quantum mechanics and the theory of general relativity. It is a testament to the power of human curiosity that a patent clerk in Bern, working in his spare time, could completely transform our understanding of the universe. So, on June 30th, we have 3 monumental events. We have the submission of Einstein's special relativity paper in 1905, the Tunguska Event in 1908, and the discovery of the blue eye pulsar in 2026. 3 events, separated by more than a century, each of which has reshaped our understanding of the cosmos in its own way. Each is a reminder that the universe is a place of mystery and wonder, and that our understanding of it is always evolving. Each is a testament to the power of human curiosity and the relentless pursuit of knowledge, and each, in its own way, embodies the spirit of Richard Feynman. Feynman once said, "I think it's much more interesting to live not knowing than to have answers which might be wrong." This is the essence of the scientific attitude. It is the willingness to live with uncertainty, to embrace the mystery, to keep asking questions even when the answers are elusive. The Tunguska Event is a perfect example of this. We still do not know exactly what caused it. We have theories, but we do not have certainty, and that is okay. The uncertainty is part of what makes it so fascinating. It is a reminder that the universe is not a closed book. It is an open question, waiting for us to ask the next question. The blue eye pulsar is another example. For decades, CCOs were considered to be radio silent. They were a puzzle, a mystery. And now, we have solved that mystery. But the solution has opened up new questions. How many other faint young pulsars are hidden in the Milky Way? What other secrets are the neutron stars keeping from us? The discovery is not an ending. It is a beginning. So tonight, as you look up at the stars, think about the Tunguska Event, the day the sky exploded over Siberia. Think about the blue eye pulsar, the dead star that has just started speaking to us. Think about Einstein, the patent clerk who rewrote the laws of physics. And think about Richard Feynman, the man who taught us to embrace the mystery. The universe is a vast and wondrous place, full of surprises. And we, the curious ones, the ones who refuse to stop asking questions, are the ones who get to explore it. Stay curious, my friends. The universe is speaking. And we are finally learning to listen.